Alrighty. So the last time we were in lecture, we were talking about. Oh, I don't have it here because it was in my different laptop. We are talking about AHP. Okay. And we started talking about how can you figure out if somebody's decision matrix that they get, or not decision, comparison matrix is consistent or not. And we started presenting a methodology for doing that. So in this lecture, what we're going to do is we're going to apply that methodology and actually figure out, for a simple case, whether somebody was being consistent or not. So let's go ahead and make that happening. Decision making. Okay. So just to review, we're going to start off usually with some sort of A matrix. And it's going to be diagonal. And then everywhere else, we're going to have some sort of values. Okay. And the first step is to normalize our matrix. By dividing each column of A by its sum. Okay. Once we get that, we're going to have a matrix that kind of looks like W11, W12, W13, W21, W22, W23, and this will repeat onward. And we know we have consistency if for each row we have all the values equal to each other. Okay, so across this top row, we would have W11 equals W12 equals W13. Across the bottom row, we'd have W21 equals W22 equals W33, or sorry, 23, and so forth. And so, of course, if we have more factors here, we just considered, here we only have 3 factors, you can tell by the columns. But the more factors you have, this square matrix is going to grow, and you just want to make sure that all the values are the same across. Okay, so let's actually apply this to the problem that we stated before. So we had something where we are talking about a laptop. And I had asked somebody a few questions about what was more important, battery life, CPU, memory, and so forth. And what they said was the battery life is 2 times more important than CPU. All right. They also said that CPU was equally important as memory. And finally, they said memory was 3 times more important. Than battery life. Okay. All right. So we asked some folks these questions, and these are the responses that they give us. With that, we end up with an A matrix that looks like the following. So we have 1, 1, 1 across the diagonals. Let's assume the factors go something like battery, CPU, memory. Okay. All right. So battery life is twice as important as CPU, so we're going to see a 2 there. All right. And we see that memory is 3 times more important than battery life. And so that tells us we're going to have a 1/3 there. That would put a 3 on the bottom. Everything's sort of like a reciprocal mirror image. Okay. And so at this point, we're just missing this last value. Oh, let me actually make it look like a square. Okay, so we're missing CPU and memory, and these are equally important, so we put a 1 and a 1. All right. So to go through this sort of procedure, the first thing that we do is we sum up all the columns. So here, if we take the sum, we get 4.5, right? And the next one, we get 4. And this last one, we get 2 1/3. What is 2 1/3 in fractions? In fractions, 6 7/3. 7/3. Okay. So if we want to calculate n, what we're going to do is we're going to divide all the values in this first column times 4/5, which is just 9/2. Okay. And so we're going to end up with 2/9, 1/9, and 2/3. Is that right? I think so. 2/3. Taking the next column, we're going to divide 2, 1, and 1 by 4. So we'll get 1/2, 1/4, and 1/4. Okay. And finally, we're going to divide the last column by 7/3. So we end up with 1/7, 3. Oh, no. 7/3. Or 3/7, sorry. And 3/7. Okay. So the first thing we do here is we look across the rows. Okay. Do we see the same value across the first row? No. Same value across second row. Third row? No. Right? So none of these are consistent. Okay. That said, sometimes we'll say, well, let's take the average weighting of these guys. Okay. So in order to take the average, to figure out what the average weighting is, okay, that's W1, W2, and W3, averaged, right? We do 2/9 plus 1/2 plus 1/7 divided by 3. 1/9 plus 1/4 plus 3/7 divided by 3. And finally, 2/3 plus 1/4 plus 3/7 divided by 3. Okay. In some ways, you could probably do this in Excel pretty quickly. So we can sort of mock that up pretty fast. So if you guys have a problem maybe with more values or something like that, we can sort of figure this out. But that said, I'm going to show you an alternative way of doing this using eigenvalues and eigenvectors. Okay, so I think, what did we have for this problem? 1, 2, 1/3. 1, 2, 1 divided by 3. 1 divided by 2. So this was our matrix, right? Something like that. So we could easily take the sum down each column. All right. We already have this. Okay. Then we can normalize everything. So we're going to take each column and divide it by the same sum at the bottom, making sure to do a $sign. Okay. And then we can do that down. Okay. And again, we sort of see the same idea that we don't get the same sums going across the rows. But if we want to calculate the average W, so let's say average W, we're just going to take, is it average? Yeah, cool. Tab? Yeah. We're going to take an average of the values across, okay? So this is our weighting W, okay? So when we fill out the weightings in our AHP table, these are the values we can use. And we can see that, in fact, these should add up to 1, as we kind of expect our W's to do. Okay, so that's just a quick way. If you ever have a bigger one and you want to not calculate it by hand, just to make sure you don't make a mistake, that's how you do it. So it's nothing too bad. Now, I think I mentioned in the last class, what is really the definition of consistency? Let's put it this way. The way that I always think about it is, let's say you like baseball and you're like, I like the Braves better than the Yankees, and the Yankees better than the Red Sox. Okay? If that's the case, you better like the Braves better than the Red Sox, right? Okay. So people do this also in election voting, right? Like, I don't know, let's say you like Bernie Sanders better than Elizabeth Warren, and you like Elizabeth Warren better than Buttigieg. Then you better like Bernie Sanders better than Buttigieg. But that doesn't always happen with people, right? That would be inconsistent if that wasn't the case. And so we have a similar definition for checking for consistency. All right, so perhaps a more formal one is the comparison matrix A is consistent if Aij times Ajk is equal to Aik for all I, J, and K. All right, so what are we saying here? So this is like saying, well, if battery life is twice as important than CPU, and CPU is twice as important as memory, then your battery life better be 4 times more important than your memory. Okay? And all that we're doing is we're saying this relationship has to hold for all combinations in all orders. Okay? So that's the consistency. Okay, so there's a more formal way of stating it, and it just so happens that if we have the same values across each row, then we know this must be true, right? That we have this consistency. All right, cool. All right. All linear matrix problems are always fun because we can apply linear algebra to them, which is one of my favorite areas. And let's sort of look at what happens when we take this approach and we complete the following multiplication. So I'm going to take our comparison matrix A and multiply it times W. Okay. And so what we're going to show here is another method for determining whether a matrix is consistent, and also it's another way of calculating what is the average W. Okay, so for now we're going to assume that we don't really have any values for W. We're just going to fill it in with variables, but we do have the values for A, let's say. Okay. And so I'm just going to do this for a 3x3, but it scales up to any size. Okay. So again, typically we'll be given this A matrix, right? So in our case, it was like 1, 2, 1/3, 3, 1, 1, and I think 3, 1, 1. Okay. We're given this matrix, but we know that A matrix is really the ratio of W1, W2, and W3 with each other. Okay. So usually, again, this is given. Okay. Now the thing is, we don't know the specific values of W1, W2, W3. But what we're going to do is say, well, let's pretend we are to multiply A times W1, W2, and W3. What happens? Okay, so we just do our standard matrix multiplication. We take the first row and we multiply it times the column vector. So can somebody tell me what we get in the first element? Plus W1. All right. For the second element, we get W2 plus W2 plus W2. And for the third one, we get W3 plus W3 plus W3. Okay. All right, so if we can simplify this, it ends up as 3W1, 3W2, 3W3. Okay. All right, so I'm going to do one more thing. I'm going to rewrite this a little bit differently. So now we have A times W. All right. And anybody want to guess where this number 3 comes from? How many factors do we have? 3. Okay. Sort of makes sense. Okay. So if you had a 4 by 4, like 4 factors, then you would see 4W1, 4W2, 4W3, and then 4W4. Okay. So we're going to see something. If we do this multiplication, we're going to have an equation that looks like this. All right. Now let me rewrite this equation in something you might have seen a little bit before. What if I were to write it like this? What does this remind you of? Does anybody know what this is called? Yeah, eigenvalues. So it's really weird, but this is called the eigenvalue problem. All right, so if you guys took matrix, eigenvalues come up all the time. And a lot of times, the solution to the quote-unquote eigenvalue problem tells you something. So in fact, what we're doing here is if I give you a matrix, A, okay, and you solve for W and lambda, okay, by solving the eigenvalue problem, then in fact what you're solving for ends up being quite useful. It does two things. One, it will solve for W bar. Okay. Additionally, it's going to tell us if A is consistent. Okay. So the way we're going to know if A is consistent is if lambda, the solution, or the eigenvalue that we solve for here, if that's equal to n, the number of factors, then we're consistent. Else, if lambda is not equal to n, then we're not consistent. Okay? So this ends up being an easier way because you can just type in a matrix into your calculator and solve the eigen. Do you guys have graphing calculators that can do that? I think most of you all do. So you can just type in your matrix and say, hey, solve for I. With that in mind, I'm going to tell you guys now, this is one of those classes where you will benefit from programming calculator, and it's almost required for the exams. So if you don't have one, please make sure you find a friend who will let you borrow one for the exam and use it, or check one out from the library, okay? So I'm going to say this again. You are basically required to have a programmable calculator for this class when you take the exams, okay? Not so much for this, but later on in the semester, trust me, it'll make your life a lot easier. Okay, so let's actually see what happens when we solve the eigenvalue problem. Do I have MATLAB? Oh. All right, so I have Octave. I'm sure some of you have worked in MATLAB. Octave is just the free version of MATLAB. Okay, so can somebody, let's see. What did we have for our matrix? 1, 2, 1/3. Okay, so let's actually show how we would do this. So whether it's in your calculator or in Octave, it's basically the same. So in Octave, you do it at home if you wanted to. We would just type in our matrix. Okay, so there's our comparison matrix that we had before. For MATLAB, we can use the eig function to calculate our eigenvectors and our eigenvalues. So maybe I'll just call this lam. Okay, so this will give me the lambdas. Oops. 1, 2, 5. Okay, so I'm going to move this over. Okay. So I'm going to focus in on these lambdas. Okay, so we're going to pull them out. And they're the diagonal elements of the lambdas. Okay. So this first one is a whole number with no imaginary part. But now our next two eigenvalues are complex numbers, right? They have imaginary parts. And so it ends up that our consistency, so we would expect an eigenvalue to be equal to 3, but in this case, the only real number that we have is equal to 3.36. Okay? So the fact that the eigenvalue is 3.36 and not 3 confirms the fact that, in fact, this comparison matrix is not consistent. Okay? So that's one way we can check it. Or that is the way we would check it. Okay, so now I'm going to pull out the eigenvector that is associated with that first eigenvalue. And the place that we get it is by looking at this first column right here. Okay, so unfortunately MATLAB does not normalize the columns, but I'm going to pull it out real fast. Okay, so this is the first column. Okay. You can see these numbers don't add up to 1. I think when you solve the eigenvalue problem on your TI-80 whatever, these values should add up to 1. In this case, we have to do some normalization. Oops. So I'm just going to divide that vector by itself. Okay. What we see here, so after we normalize it, so they all add up to 1, all right, we get 0.28, 0.255, and 0.463. Okay? So what I'm going to do is we're going to verify that that's exactly what we get in these three values here. Okay? So I'll go ahead and break out my calculator. We'll see how this goes. Where's my calculator? All right, so 2 divided by 9. Actually, no, why don't we just... Oh, no, we have it in Excel. Why am I even wasting my time? Bam. Let's see. So what did we get in MATLAB? Oh, why is it different? It should be the same. Did I type something in wrong? Ooh. 1, 2, 1/3. Did I type it in wrong? Man. 1, 2, 1/3, 1/2, 1, 1, 3, 1, 1. Oh, that's very odd. I'm going to have to get back to you on this. I should be giving you the same answer. Okay? Either way. So we'll follow up with you on that, on why it's giving a different answer. Maybe I typed in something wrong. But okay. So let's pretend we did this all right. Okay? Again, we're getting two pieces of information from this. We're getting an average weighting, okay, a W1, W2, W3, okay, from solving the eigenvalue problem. And we're also getting the eigenvalue associated with it, okay, 3.367. Okay. So 337. Okay. All right. Okay. So this is the solution to our eigenvalue problem. All right. Now, we've already established that lambda, it's not equal to 3. So we know it's not consistent. Okay. And again, we already established this when we did it the other way. All right. So why is this method particularly important? Well, one thing that we can do is we can talk about how consistent somebody is. Are they wildly inconsistent or just a little bit inconsistent? And we do that by using something called the consistency ratio. All right. And that consistency ratio is given by the consistency index, which we call CI. All right. All right. And RI, which is the consistency of a random matrix. Okay. So sort of give you an idea of how we calculate that. Okay. So this first, the consistency index of the matrix we had, is given by the lambda we found minus the number of features divided by n minus 1. So in our example, our CI is equal to 3.37 minus 3 divided by 2. I don't know what that is. Yeah. 0.185. Okay. All right. Now, this RI it's actually really neat how they did it. There's a whole paper. Basically, they generated a whole bunch of random matrices and calculated what the average consistency index was. Okay. So if you have a random comparison matrix, what is the CI for that random matrix? Okay. And what they found is that on average, for a random matrix, the consistency is given or can be approximated by the following equation. All right, so 1.98 times n minus 2 divided by n. Okay, so this was a neat little finding that people had. Okay. All right. So for this particular example, it's actually pretty simple, right? So we have 1.98 times 3 minus 2, which is 1, divided by 3. So it's just 1.98 divided by 3. .66, yeah. Okay. So now that we have these two numbers, we can actually calculate the CR. So we're going to take this 0.185 and divide it by 0.66. All right, so we got something like 0.28. Okay. Okay. So is that good or is that bad? Well, now this isn't my area of research, so if you ask me why did they do that, I can't tell you. Okay, but basic premise is this. You want your consistency ratio to be as low as possible. Okay? So if your CR is less than 0.1, the level of inconsistency is deemed acceptable. Okay. So in this case, we have a value of 0.28, which is greater than 0.1. So it'd be pretty fair to say that, this person is actually inconsistent. Okay? But if you got something like 0.05, 0.8, 0.0001, you would say they're relatively consistent, or the level of inconsistency is not considered problematic. Okay? So you can't actually say they're consistent unless they are consistent, but you can say their inconsistency is acceptable, if that makes some sense, right? Nobody's perfect, but you're good enough. It's kind of the idea. All right, so that's everything we need to learn about AHP and how we understand and rate people's sort of decision-making process. So, cool. We're actually doing pretty good. Yeah. So I'll follow up on what the issue was, why it wasn't matching. They should be matching, I think, and we'll get to that. But accept the methodology as both of them being correct. Okay. So at this point, we're going to jump into another technique for making decisions. So AHP is basically just a methodology for how we can make decisions when we're weighing different criteria. Okay. Now, there were a few issues that we had pointed out before that were kind of worth considering. One is, how do we set these decision weights, right? If we do set these decision weights, are they even consistent, okay? And I think these were actually sort of important issues that we need to address. One of the things that AHP doesn't necessarily take into consideration, though, is randomness, okay? So it's making decisions assuming that the weights are correct or true. So what do I mean by that? So in the previous problem, we were talking about, I think, Martin and Jane, all right? And we are talking, let's say, about they made a decision based on location and reputation, okay? And I'm going to focus in on the location aspect. They said, okay, for University A, see, I think I have the numbers here. I give it a location score of 1.29, University B, 277, and University C, 594. Okay. All right. How many of you guys are from Orlando? Okay. How many of you guys are not from Orlando, like far, far away? Okay. So, let me ask you this. Did your conceptualization of Orlando before you came to Orlando match the reality? No. All right. Sort of, kind of, probably not perfectly, right? Because none of you, well, the majority of you didn't live here or grow up here, so you don't really know what Orlando's like. So we have Martin, who somehow said, yeah, the location of University A gets a 1.29. How does he even know that, right? University B, 0.277. There are things you think about a city, right? You think, oh, I think Orlando's this big, fun city with lots of cool places to go out. And then you get there, and it's even better than that, right? And in fact, so maybe it wasn't, before he thought it was a 1.29, but in reality, it might be a 0.6, okay? So one of the weaknesses of AHP is that it assumes a certainty in these values, right, that might not exist, okay? So that's another sort of weakness. Besides figuring out even the weightings, we assume that we have perfect knowledge about these values, which in a lot of cases is not really true. Okay. So that's why, when we talk about stochastic OR, really what we're interested in is what happens when you do have uncertainty. And how do you make decisions in face of that uncertainty? Because the previous method, there was no uncertainty, right? You came out with an exact answer that you assumed was truth and true, right? But really, the world is a lot more fuzzy than that, right? And so with that, we're going to introduce another method called decision trees. Now, these are different types of trees, so try not to confuse them, right? And what they're going to focus on is if you make a decision, how that decision might be, or the result of that decision is affected by randomness in the world. And we'll study it through sort of a simple problem dealing with investments, okay? All right. Okay, so we're going to talk about investment decision making. All right, so let's say your grandma gave you $100, or she did to you what I do to my girlfriend, which is, hey, here goes 2 gifts, pick one, right? Which I learned women do not like. You end up having to give both in the end. But let's say your grandma did that to you. She goes, I have $100 for you, and we can either invest in stock A, or just say invest in stocks, or we can invest in bonds. Okay, so for those of you who don't know, bonds tend to be quite a bit more stable, right? They might not get you a lot of money. They're almost guaranteed returns, but you're not going to lose money. Okay, stocks could be anywhere, right? If the stock market goes up, hey, awesome, right? Or I don't know, stock market goes down, we have another dot-com bubble, then you've lost all your money. Okay, so, and so the idea is we have this investment decision to make. So this is our decision. Right. Now the issue is the return is based on what the stock market does, okay, or what the, let's say, economy does or the market does, okay? And so what we're going to say is maybe we'll have a bull market, or we're going to have a bear market, okay? Which one's good? I always forget. I think it's bull. Yeah. So let's do it. I think that was the case. Yeah. Let's do green. So this is good. This is bad. Okay. So if you just want to think of it as good and bad, that's fine. Okay. We'll just think of it as good and bad. Okay. Alrighty. Okay. Now we're going to assume that, hey, usually life is pretty good, and the probability that a bull market happens is 0.6. All right. So let's say 6 months from now, we're in a bull market, you're probably going to make a lot of money in your stocks, right? All right. And we'll say the probability of a bear market is 0.4. Now the problem is if we have a bear market and you invested in stocks, you might end up losing a lot of money. All right. So we're going to sort of represent this. Let's see. We can represent this using a decision tree. And so we're going to start at some point here, and we're going to make a decision. So the first one is going to be invest in stocks. The other option is invest in bonds. Okay. Now the important thing here is that you're making the decision before watching what unfolds. Okay? So you don't know what the economy is going to do. That happens after you make your decision. So let's say you invested in stocks. From that point, we have two options. We can either have a bull market, and I'll do that in green, or we can have a bear market. Okay. If we have a bull market, let's pretend your $100 becomes $5,000. Awesome. All right. But if you were in a bear market, then you end up losing $2,000. Now, bonds, I said they're a little bit safer. So we're going to go through the same process. We say, all right, we invested in bonds. We have two possible outcomes that could occur. Again, we have the bull and the bear. And we should actually associate the probabilities with that. All right, so we're going to have 0.6 here, 0.4 there, 0.6 here, and 0.4 there. Okay. So when you invest in bonds, they're a lot safer. So in the bull market, you're going to make $1,500. And even if things go south and the economy is bad, you still end up ahead. You make $500. Okay. So, show of hands, who would invest in stocks? Bonds? You guys are taking the 500, right? It's not bad. So it's guaranteed. It seems like you're guaranteed money at least. Okay, so the way we normally use decision trees is to calculate the expected reward. Okay. And it's not just the expected reward, it's the expected reward of each decision. Okay. All right. So let's sort of see how this works out. So what I mean by that is we're going to say, well, what's the expected reward if we invest in stocks? And I'm going to just put a variable x right there for now. And what is the expected reward if we invest in bonds? Okay. So when we're taking expectations, we take the expectation against some randomness. So what's the randomness here? The what? The market, right? Whether it's a bull or a bear. Okay? And so what this X represents is the type of market that we have. Or we should say that occurs. Okay? And the type of market that occurs is, random. It's a random variable that's unknown. Okay. All right. So we want to figure out our reward in stocks over all the possible outcomes of our random market, and we want to calculate the expected reward, how much we expect to get if we invest in bonds. Okay. So with that, we need to actually write out what are the reward functions. Okay. So we kind of have it in this tree already, but I'm going to make it a little bit more explicit. Okay. So our reward in stocks is either $5,000 or negative $2,000. Okay. It's $5,000 if X, right, our economy is a bull market, and and it's negative $2,000 if we have a bear market. We can do the same thing with bonds. We get $1,500 when X is a bull market, and we get $500 if X is a bear market. So the other piece of information I already gave you, but I'm going to write it a little bit more explicitly so we can use the equations we've learned before, is we need to know the probability distribution over the bull and bear market. Okay. So it's just 0.6 and 0.4, right? And 0.6 refers to the probability that we have a bull market, while 0.4 refers to the probability that we have a bear market. So usually in a problem, these are the sort of pieces of information that you need. You need a probability distribution, okay, on the different events that can occur, and then the reward function for each of the decisions. Yes, ma'am?
Is it not possible for it to be like a continuous variable? So like
Absolutely. Yeah.
possibly half and half?
Yeah. So you would use the continuous equations for calculating reward functions instead of the discrete. Yeah. And I think there's probably a homework problem for this coming homework that involves that. I just don't do it because it takes too long to work through an example problem in class. But more or less the same idea. Okay. So again, our goal is to calculate the expected reward. And so we can just start by writing down, well, what's the equation for that? All right. Well, it's given by, normally, remember, the sum of x and the set of all x times the probability of x times whatever our reward function is of x, okay? So we can actually start filling out some of these options so they make a little bit more sense. Okay. So it's not just the summation of x and x. Really what we're talking about is saying, well, what happens when x is bull and what happens when x is bear? And we're going to plug in those values. Okay. So we'll go through the summation. First, we plug in bull, right? And we take the probability of x, where it's bull, times the reward of stock, where it's bull, plus the probability of bear, times the reward that you get investing in stock when you have a bear market. So at this point, we can plug in some stuff. So I think we have, what, 0.6 times 5,000 plus 0.4 times negative 2,000. All right. Just going to calculate that really quickly. Oh, 2,200. Not bad. All right, so our expected reward. All right, if we invest in stocks is $2,200. Does this mean we'll actually get $2,200? No, we either get 5,000 or we lose 2,000. You can't actually get this value, all right? But the idea is if you were to do this lots and lots and lots and lots and lots of times, that on average, that's what you'd end up with. But you can't really do this. This is the problem with decision trees, right? How many times can you make this decision? Well, no. No. But it has to happen at a different time, right? because the event is like 6 months later. What's going on? So every 6 months you can make this decision, sure. All right, but how often maybe could you guys lose $2,000? So it's kind of a weakness. This, even though we're calculating the expected reward, this kind of makes the assumption that you can replay this game. But the reality is, if you only have so much money, you might not be able to replay this game, right? You lose $2,000, I get your legs, right? Type of deal. Okay. Okay, so we can do the same thing to calculate the expected reward for bonds. All right, so we're going to go through what's the probability of having a bear or a bull market, and we're going to multiply it times the reward of investing in bonds when it's a bear or bull market. Okay. All right, so if we plug stuff in, what did we have? .4 times 500 plus 0.6 times 1,500. Okay, so I'm going to calculate that guy real fast. $1,100. Okay, so what did we do here? We said, let's make a decision about whether we invest in stocks or bonds, and calculate what is our expected return on investment, let's say 6 months from now, and we're going to see which one's bigger. Okay. All right. So in the first case, or in the case of stocks, we expect to make $2,200. And in the latter case where we invest in bonds, we make $1,100. If we were to use the expected probability, or expected reward, which decision would be smarter? Yeah. Okay. So this technique can be used everywhere, right? So you're playing poker, do I double down, do I split? Right? You can go through and calculate the expected return based on each decision. Okay. All right. The way we posed it, for starters, we assumed that you only had 2 decisions, okay, stocks and bonds, and that there were only 2 different outcomes, bull and bear. Okay. And Alexandria, yeah? Yeah, she sort of asked the question, well, couldn't you have more than 2 decisions? Couldn't it be a continuous distribution? Absolutely. Okay. Now, typically, when you're working with decision trees, you're going to have a fixed number of options, okay? So that is options in the decisions and options in the outcomes. But methods still kind of work out the same, okay? So you can actually Alright. So are stocks and bonds the only decisions that you could make to invest your money? What else could you invest in? Real estate? What else?
Education.
Yeah, education. I was going to say a kick-ass party, but yes. Education. All right. So, like, I was just watching. Did you guys ever see Parks and Rec where Aziz runs his business to the ground, and like they have $10,000 left, and they decide to throw the world's greatest party. Anyways, okay. So like we start with the decision. There's nothing to say that you can't have any number of options, right? We just presented it as 2, but you could have 50 for all we care. Okay? Not only that, so let's say I look at one option. So, in the stock one, maybe we end up with 2 outcomes, bull and bear. Okay. Let's say another option was to invest in your education. Very, very wise. Okay. There is let me just say, whatever happens here, so here we have bull and bear as the process. Doesn't mean it has to have the same process here. Okay? So maybe for education it could be like you picked a major that becomes very hot when you graduate, right? So maybe it's like pick the right major. And what I mean by that is you pick the right major for the economy. Okay, not like, yeah, pick the IE. Alternatively, we could have like various levels, right? Maybe it doesn't matter what major you pick. But the idea here is that even the distribution, according to one of the decisions, does not have to be the same there. Doesn't matter. Okay? But you can still go through and calculate these probabilities. Okay? Because really, if you look at what these equations are doing, they're just multiplying the reward times the probability of that reward happening, right? 1,500 times 0.6, 500 times 0.4, and then adding it up, okay? And so this is sort of a general principle, right? So if you want to calculate the expected reward for some variable x where you're making some decision I, right? So first, decision 1 was invest in stocks. Decision 20 was invest in your education. Okay. If we want to write the mathy version of what we're doing, we're just looking at, okay, let's say we did invest in your education, right? What is the probability of all those outcomes here? Okay, so you picked the right major, occurs with probability P1. You picked an okay major with probability P2. You picked a terrible major, and you quit school, right? I don't know. Political science, yeah, who knows? Actually, poli-sci, you can do pretty good. I think all majors you can do well, right? It all just depends on how you maximize it, right? But, let's just pretend, right? So we're going to go through these options, P1, P2, P3, P4, the possible outcomes that could have occurred, right? And we're going to multiply it times whatever the reward is associated with that outcome, okay? Okay. So here we had P1, P2, P3, and that led to making, I don't know, $200,000 a year, all right, $100,000 a year, $50,000 a year, or massively in debt, all right? Okay? So, you also picked the wrong school, right? Who knows? Or you decide to become a doctor and then didn't want to practice. Right? That actually leads to a good example, though, because we can talk about what happens with chained decisions, right? So again, what I mean to say here, just to be clear, these Aij are the 200,000, the 100,000, the 50,000, and the negative 500,000. You're just multiplying the probability times the amount and then summing it all up. Okay, and that's how we calculate our expectation. All right. So let's actually think about this maybe a little bit differently. So let's focus in on this education. Let's say you get to UCF. Yeah, so I is the decision. Yeah. So the decision I. And so this is for a simple case where we have this called a single stage process, right? You make a decision, you wait for something to happen, and then you get a reward. That's a single stage. So what we're now going to talk about is you can actually use decision trees in multi-stage decision making, okay? And so we're going to do this with, I'm sort of doing this off the cuff, so it might be a little bit off, picking your major, okay? And we're going to sort of figure out, okay, if you pick your major, what can you expect your annual income to be? All right. So let's say you got to the university. What majors did you guys consider? Give me like 2 or 3. So IE, obviously.
Systems engineering.
Nope. Systems. Is that a major? No? Okay, then we're gonna do marketing. All right, give me one more.
Aerospace.
Aero. I like aero. Okay. You heard liberal arts in there. You got a few. So there's clearly a whole bunch that we could do. All right. Actually, did any of you start with another major besides IE? What did you guys start with? Aero. Mechanical. So we're going to change this to MAE. Okay? All right. So this is a decision that we're making. So a lot of times, actually, the way that we denote a decision is we actually use a box. Sorry, let me turn this off. It's distracting me. There. All right. So we made a decision on what major we're going to have. Okay? The decision you make as a freshman, what do you think that you actually graduate with that major? Actually, does anybody know what the average... cell phone away, because I can see it. Sorry. If you were hidden better, I wouldn't have seen it. Okay, so how many people, or what fraction of people do you think keep their major over their academic career? 21. Better than that. 7%. So on average, I think somebody changes their major 1.5 times in their academic career. Does that sound about right to y'all? Yeah. So most people will change their major once, right? Although not everybody does. So it ends up, I think, if you work that out, I think only like a third keep their major. But this is across the United States. Okay? So in fact, the first decision that we have here is what major you choose. But then we have some outcomes, right? Which is, what is the probability that you end up keeping your major? Okay? And so usually in our decision trees, when we have a random event, we represent it with circles. Okay? Okay. And so this random event is going, for us, it's going to correspond to graduating in your major, okay? Or changing majors. Just for, well, yeah, okay. So let's say we have this option, you graduate in your major in IE, okay? All right. Or you change majors. Grad, change. All right. Do you think the probabilities are the same for all these majors? Yeah, some of them are higher and lower. Okay, so let's say 70% of folks graduate who start in marketing, graduate in marketing. Well, what's a major, everybody? Well, no. We'll just say changed major, okay? Well, 30% changed their major, all right? For IE, what fraction do you think keep it? Let's make it up. 0.6, and then 0.4. And for MAE?
20.
Yeah, it's, I don't know what, I actually have the statistic somewhere, but I'm certain MAE is one of the lower ones. Actually, does anybody know what the worst is? In engineering, it's pretty easy, or in our college, computer science, yeah. Or computer engineering, I think they have the lowest retention rates. Anybody know what it is for the university? What's the hardest major? Or hardest class you guys ever took? What? Dynamics? Well, physics and math.
Calculus too?
Yeah. So physics and math have the highest, or we call it the lowest retention rates for a major. It's actually kind of funny. So I do education research, and I do it with the physics professor, and we are talking about people changing majors is good or bad. So when people, let's say you come in as a physics major and you change your major, what major do you think they go to the most? Engineering. They come to engineering. Okay. And so I was talking with this physics major, and she goes, changing majors are bad, like we want them to graduate in physics. And I go, wait, so you think changing majors from physics to engineering is a step down? And she goes, I'm like, okay, that's fine. We'll skip this discussion. But understood. I was like, I thought they were just finding a major that matched them better, right? Why not? Okay, so we have all these outcomes. So let's say you do change your major, okay? You have the opportunity to make another decision, right? And what's that decision going to be?
Grad school.
Well, let's say even before grad school. What major you change to, right? Yeah. 0.4. Okay, so I'm just going to do this for one case. But you could make another decision. All these guys can make a decision on what major to change to. Okay. So what does IE go to normally? Business? Is there another major? CS? I'm sure very few people do that. But let's pretend, right? What do marketing people do? Well, we have to give them two options because there's a decision, but we'll put that in there. We call it early entrance to the workforce. What's the other option besides marketing? Communications, yeah. I had a marketing student tell me they wanted to do engineering, and they're like in their second or third year. And I go, have you taken Calc 1 yet? And they said no. And I go, well, you're not graduating for another 7 years then. Which is the reality of our major, unfortunately, right? It does happen sometimes, right? People, they just, we all get put in a certain path sometimes. But you have a decision to make. Do you want to take 7 years or not? Okay, so MAE, they decide to change. I know we get some IEs, right? What else might they change to? Business. Okay, everybody likes business, right? Probably the smarter decision in the end. Although the classes I'm not a big fan of. Okay, so we've made a decision, IE. Okay, so now that we've made all these decisions, what do we do after we graduate? Hopefully. Yeah, we apply for jobs, right? So each one of these now, I said I wouldn't do them, but let's see. So each one of these now has a new event, all right? And this is, I applied for a job, what job do I get? Okay, so let's say you applied to business, okay? So the random event is what job you get. Okay, and specifically, let's say how much you get paid. So let's say you graduate with a business degree. How much money might you make on your first job? 40, 50? Sure, we'll do 40. 40K, 50K, and let's say there's some weirdo who makes 200K, right? And each of these is going to come with a probability. Okay, so let's say this happens with 0.6, 0.4. Oh no, that right. Say yeah, really bad. Okay, and 0.1. Okay. All right. So now let's actually do some stuff. Let's actually calculate some things. Here's the problem. All right. You can't actually ask, what is the expected reward of majoring in MAE? Okay. Why can't I calculate this value? So let's follow this path down. MAE, boom. I either graduate, and again, let's say I graduate and I automatically make 100K. Okay. I can either graduate or change. What's the problem at this stage?
You didn't graduate. You change majors.
I change majors. Right? I have another decision to make. Okay. So I can't quite calculate this probability because part of it's not random anymore, right? Yeah, there's a random event here, but in this second stage, I have the option to make a decision again. Okay? And so I can't calculate what is the expected reward of selecting MAE at the beginning because you know what? At the second stage, I can make a decision. I can make a decision about IE, or I can make a decision about business. Right? That said, I can calculate stuff like, what's the expected reward of selecting MAE given you changed majors to business. Right? That you can calculate, but we're left with what we did before, right? If we say, what's the reward of picking MAE, given that you changed majors to business, we're looking at what's happening right here. Okay, so we're going to follow our tree down. We took MAE, and we know we changed majors and we decided to change majors to business. At that point, if we want to calculate our reward, it's just equal to 0.5 times 40K plus 0.4 times 50K plus 0.1 times 200K. So whatever that adds up to, that's the expected reward. Okay? So this is we can still do a decision tree for multi-stage decision making, but it becomes harder, next to impossible, to calculate the decisions or the expected reward in the first stage. Okay? We can't really do that. So that's just something to be aware of, but we can still create these trees. Okay? And this is something we do in everyday life, right? At least when I'm driving, I go, hey, I'm going to take the fastest way between, my house in Winter Park and downtown Orlando, right? If I hit a traffic, I kind of know the side streets that I can take, right? But there are cases where I go, man, I know it's rush hour traffic. I'm not going to take my regular route because I know even the side streets are crowded. So I'm going to take a different route altogether. Okay. But you still have the option to keep making changes. All right. So anyways, we're over. Thank you, guys. Sorry. Yeah. Thank you for being patient.